Hello and welcome back to my channel, the x86 Hobby Channel, concentrating on 32-bit Linux assembler. This time I want to discuss the problem of inputting a single key press into our programs. Normally, when requesting a key press from your program, the terminal will not return anything until enter is pressed. And then what you get in a buffer, which you can read, will be all the keys pressed up until and including the enter key. However, very often in our program we want a single key press. For instance, a Y for yes, N for no, enter, so on and so forth. So we don't want to have to press any other key and enter every time. Any key press should be returned. In this video, therefore, I'm going to explain how in my programming I use a routine which will switch between a single key press input and multi-key press input, which is the default. So we switch over to single key press at the beginning of our program, and then at the end we can switch back again to multi-key, which is the default for the terminal. Okay, let's get started. So first of all, how do we normally read a key press in assembler? Well, the first thing we do is we make up a buffer, make sure we have a buffer defined, and whenever we do a system call to the kernel requesting a key press, then data is placed into that buffer. After the call, the buffer contains the key data, and then we can read the buffer to see what key has been pressed. There are basically two modes of keyboard behavior. First, the default mode. The return to the caller is made only after the return key is pressed. The buffer then contains all the keys pressed up to and including the return key. This default also echoes all key presses to the screen. You will be familiar with this on the command line. This is exactly what happens. This is the default mode, sometimes called the canonical mode. The second mode, non-canonical, returns to caller when any key is pressed with the single key code in the buffer. And it must be understood that that single key code could be more than 1 byte, but nevertheless, after any single key is pressed, you return to the caller, to your program, so you can see what single key has been pressed. The following subroutine, which I am going to explain in detail, will toddle, that is, flip between both modes every time it is called. Actually, this entails flipping 2 bits, the canonical and the echo bits, in a data structure used by the TTL driver. It will normally be called at the very start of a program and at the very end of the program to return to the default condition. Okay, first of all, let's talk about the BSS section of our program. In practice, if you're using Edlin Pro's template, this will be predefined. Now what we're going to do, we're going to use a 1 kilobyte buffer, but in fact we don't need anything like that. The buffer space actually needed by this routine is about 36 bytes of buffer space. But we're going to use the same buffer, and we can do, because it doesn't matter, we can overwrite this afterwards. We're going to use the same buffer as our key input anyway, so but that's a different story. So this buffer could be as little as 36 bytes, but I'm using 1024. Don't forget, in BSS space this is a reserved memory and is normally all zeros. It's zeroed by the operating system at the beginning of your program. The first thing we need to do is give the name of our subroutine, and the name is going to be flip KB flags. Remember, in NASM these labels or names are case sensitive. Now it's up to you whether you wish to follow that with a colon or not, or a space, doesn't matter. NASM will accept either. I tend to use colons for names of routines and non-colons, just spaces, for names of data or labels to data. But that's just me. You can use what you want. In this case I'm using a colon. Now whenever we make a call to the system, to the operating system itself, to the kernel. In 32-bit assembly we're going to use 80H hex, 80 hex. We must set up registers, and the registers we normally set up are the common registers A, B, C and D. And in this case we need to zero EBX, but in fact there's a little bit more to this, as we'll see. It will save us some programming bytes if we zero EBX to begin with. So EBX is 0, that's necessary. The next we must set up EAX to equal 36H. This is the operation required. Now notice how I've done this. LEA, EAX, EBX plus 3CH. This is a 3-byte operation. Normally to set up EAX would be 5 bytes of code where you simply move EAX 36H. Now if EAX was clean, in my definition of clean meaning only AL is affected, then you could simply say move AL 36H. But we don't know that, so we have to bring in EBX to 0 the other bits. And this is one way of doing this. Quite a simple way of achieving the same thing. With ECX, this is the function number required in order to read the data block that's in the TTL data structure. In order to read that block, we need to set it up to 5401H. Remember, H is the hexadecimal number. So we don't have much choice on this. We just simply move ECX 5401H. The next important register is EDX. That must point to the buffer. That must actually point to the beginning of our empty buffer. Well, it's empty so far. So therefore we move EDX buffer, which we've done. So it's pointing to that 1024 byte empty space. Even if it wasn't empty, it doesn't matter, it'll be full by the time we finish this operation. We then call the kernel with the interrupt 80H. Now it's important to remember, when you return from this particular call, all the registers except EAX remain unchanged. They remain exactly the same. EAX, when returned, should be 0, meaning it's being called correctly. So at this stage, when we return from interrupt 80H, it's worth remembering what your registers are. They're all the same values as they were at the beginning, but EAX is 0. Now this is what it's all about. What we're going to do, we're going to toddle 2 bits out of the whole of that 36-byte buffer. And we toddle it by XOR, and those are the 2 bits in byte 12, or the 12th byte along from the beginning of EDX, and it toddles the 2 bits. Now the 2 bits we're talking about are the canonical bit and the echo bit. We don't want it echoing, and we don't want the canonical position. Okay, so that's important. Now this means we can call exactly the same routine twice. Once at the beginning of our program, once at the end. Simply because of this one instruction here, which toddles those 2 bits. If they were on, they go off, and if they were off, they go on. All we have to do now is write back to the internal buffer what we have in our buffer. To do that, we need to move ECX 5402. Now remember that at the end of 80H, ECX was 5401. So all we need to do is increment ECX, which is a 1-byte operation incidentally. Increment ECX. So it now becomes 5402. This tells the function, 80H, as we'll see next, that we're now writing back to the buffer. However, remember that EAX was 0 when you left 80H, so we need to reset it to how it was. Now we could have pushed and popped it, of course, either side of interrupt 80H, but that's a bit overkill. We simply move, same number of bytes anyway, move AL36H. Remember, EAX is 0, so we can now move AL36H instead of using the LEA instruction which we did at the beginning, because at the beginning of the routine, we had no idea what EAX was, so we assumed it was not clean. So we move AL now 36H. Finally, we call the kernel again, which should write back to the internal buffers within the kernel of our buffer. And that should then set everything up for what we need. We finished more or less the... Okay, now we return from this subroutine. Remember, it's a subroutine we're going to call, so we need to end it with a return. And we're going to call it twice in our program. It might be worth noting register values that are returned. You might need to use them for later. Immediately after calling this, in my programs I always take note of register values. It could become useful for your next routine. However, that's a different story. So that's the routine incomplete for you to use in any of your routines to change your mode. Okay then, until next time, bye bye.